So, as the name suggests, our project deals with tubercles on F1 rear wing. The project is headed by MS RAGHAV Ganesh, Lucky PRAMEETH, and myself SHAIK DILSHAD. Coming to the introduction, airfoil is a cross-sectional shape of an object that creates an aerodynamic force when moved through a fluid. Drag reduction system is an innovative system introduced by an FIA in 2011 to enable overtaking a car closely behind another. This system lets drivers open a flap in the rear wing at specific parts of the racetrack. This flap opening removes much of the drag produced by the rear wing, adding around 15 kmph more to the car's top speed, thus enabling effortless overtaking along the straights. We aim to improve the existing design of the rear wing by investigating the influence of the tubercle leading edge on the rear wing. This inspiration from nature, we also aim to find an optimized design and optimum angle of attack on the rear wing that minimizes drag and minimizes the loss of downforce on the rear wing with leading edge tubercles and compare the results with the baseline model. Coming to the objectives, to design and analyze F1 car's rear wing with and without tubercles with DRS. Coming to the methodology that we opted, first of all, the project started with performing a thorough literature survey and choosing a wide range of relevant airfoils. 27 different airfoils were finalized and analyzed using XFLR5. After XFLR5 analysis, two best airfoils were chosen, which is GOE 464 and S1223, one for the base and one for the flap. The chosen airfoils were designed in Fusion 360 and CFD analysis was performed in ANSYS. The design was according to the FIA standards. Coming to the second phase involves design of airfoil with leading edge tubercles. This leading edge tubercles model was analyzed in ANSYS and four values were computed, which are coefficient of lift, coefficient of drag, downforce, and the drag force. The values computed for the leading edge tubercles model are compared with the baseline model, which follows by documenting the results and the project Expo preparation. You can view the XFLR5 analysis documentation here. Coming to the analysis, the ANSYS analysis involves designing of the airfoils. This is the design of the airfoils without tubercles, and this is the design of the airfoils with tubercles. Next comes the meshing. The computational domain was discretized. The governing equations were solved in coupled manner using coupled pressure velocity coupling. The convergence criteria of 1 e power minus 6 was used. You can view the input parameters in the setup here. So the results are as follows. This is the graph of coefficient of lift versus the number of iterations, and the coefficient of drag versus the iterations. The computed value of coefficient of lift is 0.58214, and the computed value for the coefficient of drag is 0.03739. This is for the without tubercles model. Coming to the model for with tubercles, the coefficient of lift versus the number of iteration graph is as follows, and the coefficient of drag versus the number of iteration. The computed value of coefficient of lift is 0.61314, and the computed value of coefficient of drag is 0.035. So as a comparison, you can see the coefficient of lift for the tubercles model is greater than the coefficient of lift without tubercles model. And coming to the coefficient of drag for the tubercles model is less than the coefficient of drag without tubercles model. So the required characteristics of an F1 car's rear wing is good coefficient of lift and less coefficient of drag, which we got in this comparison. So the novelty of the project, the unique concept of adding tubercles to the rear wings. Coming to the conclusion, the purpose of this report is to check a better rear wing for an F1 car among the airfoils with and without tubercles. The tubercle rear wing gives minimum drag and good lift forces, which is desirable for an F1 car. Thank you.